We have a big breakthrough here. Emmanuel Abbé, all the way from Lausanne, will tell us about it.
Thank you, Abbé. Very happy to be back here. So I'll tell you about this recent results, a proof of the Reed-Moore conjecture, a joint work with Colin Sandon, who's back at EPFL. And I'll introduce the coding problem. So there's two formulations of the basic problem back from the 48 roughly. The worst case formulation, also attributed to Hamming, is the following. You basically you live in the Boolean hypercube of dimension n, and you're trying to find the largest number of vectors. So F2 is 0, 1. I think there's a stick somewhere, no, usually. Oh, this one I can. So you try to look for the largest collection of Boolean vectors of dimension n, such that you have the property. So E is a fixed budget of errors you have to fight against, and the property is that no matter which point you pick, if you corrupt it with E errors, that could be chosen in any components you want that the closest vector is still the original vector. So that's just a complicated way to state something much simpler, which is you want a perfect sphere parking of radius E. Or in other words, you want the distance of the point to be at least 2E. I'll formulate it like this because it's easier to connect to the average case formulation that we will see in a second. So now if you ask for what's the largest collection of points, this is still an unsettled problem, but you can always do a random code, which is you just draw this blue point uniformly at random in the hypercube. And if the fraction of error epsilon, if you denote it by epsilon, then a random code book, so drawing those code words uniformly at random, gives you an exponential number of code words, where the exponent is given by 1 minus the entropy of twice epsilon. So that's with random codes, it's still open to prove. You cannot beat that for binary vectors. And it's still open to obtain an explicit construction. Now, if you move to this average case version due to Shannon, you only ask to succeed with high probability when you perturb your code words. So now it's a probabilistic model, so it's going to be a question which is asymptotic. You have a sequence indexed by n, the ambient dimension, and you ask how many vectors can you pack such that when you draw one of, when you pick any of these code words, if you draw a perturbation within a ball of radius epsilon with high probability, and whether you draw it uniformly at random within the ball, on the boundary of the ball, or if you do IID Bernoulli epsilon corruption of the component, they all behave the same for what I will discuss today because of concentration on the boundary. So you just ask that with high probability, you can, the closest guy is the original vector. And this allows Shannon to shave off the 2. So if you look at the largest number of code words, it's still exponential with a better rate, 1 minus the entropy of epsilon, because now the sphere can overlap. This is no longer a sphere parking problem. And the overlap can be quite large. That's a significant increase. It's an exponential increase in the number of code words.
M is the code itself. M is the blue vector.
M is the number of code words, yes. Is the number of, yeah. So the good news here is that this now, once you shave off these 2, this can be proved to be tight, that you cannot hope to improve on that, yes.
That is a random perturbation of a random code word, or is it for any?
You can say for any code words, you want that the random perturbation takes you back to where you started. So here I think I wrote it that, but for any, yeah. Okay, so the good news is that one can prove this is tight. This part is resolved, and the question is how to obtain an explicit construction. I'll just quickly discuss where this entropy bound comes from. So H epsilon is the entropy of the binary random variable with bias epsilon. So it's minus epsilon log epsilon minus 1 minus epsilon log 1 minus epsilon. So the bound comes from simply, it's a volume bound. If you try to prove, so X is your transmitted code word, so you pick any code words in your code book and you corrupt it with this epsilon IID Bernoulli epsilon or you flip epsilon times n components, uniformly at random. That's the corruption is y. And you ask what is the probability of making an error? And the decoder that you should that is optimal, that minimizes the probability of error, is simply to pick the closest code word to your received vector. I'm going to assume that epsilon is less than half. The picture is symmetric otherwise, but if let's set that epsilon is less than half, so the closest code word is always the optimal decoder that minimizes the error probability. And so you make an error if, let's say, this was x1 that has been picked. When we do a random code, it doesn't matter who you pick. You get moved by essentially n epsilon flips. So that's the radius of where you end up. This is what you receive. If in that ball of radius also n epsilon, there was another code words, you will make a mistake. And so if the code book is completely uniformly at random with independent code words, all you worry is the probability that another code word falls in a ball of radius n epsilon by a union bound. This will be the volume of the ball of radius epsilon. That's where the entropy comes from. The total volume of the space. So that's the fraction of the volume. And that's a union bound on the number of code words. So this goes to 0 when you are above that rate, when you're below that rate. That's
when the code is fixed as well.
Yeah, that's RC means random code. Yeah. So that's just to show that with a random code, you can go all the way up here, and an argument that is not too much longer also shows that this is static. Okay, so now the focus of the talk today is to obtain code construction are explicit. And the first step that people did in coding theory is to consider linear codes. That means codes that are generated by a subspace, and you only specify the basis of the subspace. So in this case, K will denote the number of basis elements. This will be linearly independent, and the code is the span of this basis. And so there's 2 to the K going to be the total number of code words. That already cleans the problem of the memory constraint. This only takes linear memory as opposed to an arbitrary code that will already have exponential memory if you don't have structure. So at least there's no memory problem, but it's still not clear among all these linear codes which one is a good one. The previous arguments still go through for a random linear code. We can show that a random linear code where you pick the basis uniformly at random will achieve this entropic bound. And the question is, which can we exhibit one specific linear code? It's a classic needle in the haystack problem. And I will discuss what progress was known and what is still open. But one of the first code that was considered is these Adamar codes. That's really from the 50s or the very beginning. It's quite natural code to consider. I'll explain it here on an example. So in the Adamar code, the block length is always a power of 2. And we call m the log of n. Here I'm explaining it for m is equal to 3, so dimension 8. It's a linear code. So in a linear code, you always have the 0 or the all 0 code word. It's a linear code. Now, if I ask you to pick one other code words, or the most natural, no matter what's your figure of merit, will be always the all 1 vector. It's the opposite. No one will argue. I hope no one will argue on that. And then if you cannot change this one, and you have to pick one more. Who would you pick? Let's say to maximize the distance. So that seems like a natural guess. Half 0 half 1, that drops the distance from n to n by 2. If now you cannot change those two, so you greedily build, and you want to add a third basis element, there's a few vectors you can add that will preserve the distance of n by 2. This creates a simplex, if you can picture it. And when you XOR this, you get the dual simplex. So this is sometimes called the extended Adamar code. The terminology extended is sometimes used or not. But it's basically a simplex with the dual. So this code, that's a representation of how it looks. This code has optimal parameter when the number of basis elements stops at log n plus 1. If you stop here, the distance n by 2 is an optimal pair of parameters. You cannot improve that. And it's quite natural. It's like you greedily pack them without reducing the distance. If you want to go beyond, if you want to add code words, it starts to get a bit more, it's not so obvious how to proceed. And so the Golay codes and some of these codes, are very specific codes that found specific dimensions for which you can again have optimal choice of parameters, but in general, it's very hard to come up with optimal choice. This code was actually used in the 70s to transmit images from a spacecraft about Mars. So it has this good property where make it useful. So what is the read-more code? The read-more code is essentially applying the Hadamard codes recursively. It says this was great up to this specific choice of the dimension. And now we're just going to go on the support, which is half of the full domain. And here we're going to stack up a small Hadamard codes. Then we're going to put another Hadamard codes in there, etc. It's probably not the best idea, but we hope that this greedy approach is not terrible. So one way to think about what this does is that you can actually view the all one vector as the evaluation of the monomial, which is always 1, on the Boolean hypercube of dimension n. So log the ambient dimension. So this monomial evaluates to 1 all the time, of course. Then you can view this as the monomial x1 on the whole hypercube. So half of the components are 1. And this is x2, this is x3. So in fact, if you look at the columns of the 3 code words, they go through the entire hypercube because it's the evaluation of degree 1 monomial. So what we do when we iterate this is as if we do x1 times x2 because we put another Hadamard in here. So the read-more code, the basis vector are the monomials of a given degree. You stop at degree r, and you evaluate them on the hypercube, and it creates this kind of image that looks like this. So here the ambient dimension is 128. This is for the weight 16, and you see there's many more patterns now. So this is the definition, which is algebraic. It's the evaluation of because the bases are the monomials and the mixture with the polynomials that are Boolean of bounded degree.
The mixture, we mean the span of this.
The span, yeah.
The linear span.
Exactly. It's a linear code, yeah. So that's why I say this is a polynomial and not the mixture creates the polynomial from the mixture of the monomials, yeah. And the fact that you stop at the degree is how far you go, which specifies your number of basis elements, and 2 to the. So number of basis elements is how many, if you stop at degree r, you go through all these and choose I monomials, and then 2 to this, 2 to this is a total number of code words. The dimension is a ratio of 2 to the m by 2 to the r, where you stop. Obviously, the more you put, the higher you go in the degree, the more you reduce the distance, and it reduces with that ratio. So if you look at the regime which we care about for the first slide, when epsilon is constant, the fraction of error, we know that we can get to a constant rate, this 1 minus entropy. So to get to a constant rate, we want this r to be m by 2, so plus maybe plus square root of n times the constant. But if for a moment, let's just assume that we care about r is m by 2, then the rate is exactly half. You exactly have n by 2 vectors, right? You have half of the full space, so that's a rate of half code. That's like the regime we typically like. And so for that regime, you will see that this distance is essentially root n, because it's m by 2 here. And that's not the best distance you can hope to get. It's still a quite good distance. It's not easy to get root n distance, but there are codes that have a linear distance in n. So we know that this is not an optimal distance. However, distance is not the key for average case coding. It's the key for the Hamming formulation, the worst case, but in average case, when you only care succeed with high probability, distance is not what matters the most.
So wait, I want to ask instead of you if there are any questions, because
Yeah.
this was for some it may have been fast. Anybody? It's not clear. Everything is clear. You want to, okay.
Distance is not the key because we're not doing a worst case, and if there are a few code words that could be close, as long as with this high probability phenomena doesn't get disrupted, we are fine.
We want the points that are in more than one ball to be a small measure.
Yeah, exactly. Yeah, it's kind of you want this overlap region, the overall measure should be under control. Okay, so in fact, people realized quite early on that for this average case for a version, these read-more codes were quite good. It was first reported in the literature in the 60s. There was a talk that made the claim strong. So from what I understood, in the 60s, okay, to verify whether this code is good or not was not so easy in this error model, because to do the closest distance is not something you implement. So it's not so clear. The beliefs were from the 60s that there was a work by Lean that made the claim quite explicit, that they seem to be actually good in a Shannon setting, and then a line of work by Doomer and Farrell also strengthened the conjecture to a broader set of channels. It was again made explicit in the review paper by Costello-Forni, and then when the polar codes came, which I will discuss a bit, which are a close cousin of the Reed-Muller codes, then there was really strong hope that they could achieve capacity. And so the conjecture reported from the 60s is that, at least for the error channel, no matter what is the error rate, if you take a sequence of Reed-Muller codes that have asymptotic rates below this Shannon capacity, so this volume bound, then they will be actually decoded with hyperbolic correctly with the optimal decoder. So it's an explicit construction that has the same property as the random codes. And then there was conjecture that this was true not just for these error channels, but for any symmetric channels. And maybe the ones that are most common is either the erasure channel, where you don't flip components, but you put an erasure symbol. And so that's the simplest channel, because you know that there wasn't something went wrong, but you don't know if it was 0 or 1. And then another one that matters for application is this Gaussian additive noise channel, where you have 0, 1 that perturbed by a Gaussian and you want to reconstruct. So for all of this, it's conjecture that the Reed-Muller codes is optimal. And in fact, it has a nice property that it's the same code. It only needs to know the rates, but it doesn't care what the channel is. Okay, so this has been tackled with different approaches. I'll mention this briefly now. The first one, maybe the more classic one, is through the weight enumerator. There's two kinds of weight enumerator techniques. One called more combinatorial, based on building these epsilon nets. And the other one is using properties of the hypercontractivity of the noise operator. I'll tell you now briefly what I mean by weight enumerator. So let's go back to the second slide with this volume bound. And in the case of a random code, we said all we care is that you fall in the volume. You don't want to fall in a small ball for a new code word. Now let's go back to this picture. Because the code is linear, I'm going to assume that x1 is 0. In the case of a linear code, any code word has the same treatment. So you can assume that you transmit 0 code words without loss of generality. And so this, the corrupted code word is simply the noise in this case, because it's 0 plus z is z. And so we cannot just say anymore that because the code words are not independent, uniformly random, it's not just falling in that bowl. However, you can still ask when you try to understand the probability that there's someone in that bowl, and these are now worst case, these are the Reed-Muller code words. You can still say, what if I do some kind of union bound, but I treat at least all the code words that have the same weights equally? Because each time a code word, for example, x2, x3 has the same Hamming weight. For example, here they are on the same Hamming weight. So I'm counting how many ones the code word has. Because there's a permutation invariance, you can treat them equally, and so you can do some kind of union bound where you count how many code words of relative weight rho. So rho is a number between 0 and 1. It's the relative weight of the code word. So 30% 1, 70% 1, etc. You bind them together, and then each time you have that the relative weight is rho, then you will make a mistake if you flip. So because we assume you start from the 0 code word, if you flip half of this coordinate rho n, then you will get closer to these code words. So the budget you have to flip is half of rho n, and that you can estimate quite directly. It's so there's n row component to flip, and you have to flip at least half, and then the probability of flipping is epsilon. So you have to flip. You have to flip exactly. That's if you flip exactly half of them, and this dominates your error probability. So you can work out bounds that look like that. And then the whole work is to identify this A of rho, which is called the weight enumerator of the Reed-Muller codes, or of codes in general. And this has been a topic that has been also active. because it applies to this, but also in its own, it's an interesting quantity. And there were various results. The first one were by Sloan Berlekamp, who fully characterized the weight limiter for the degree to be 2. Then there were improvements. Then there was a breakthrough by Kaufman, Lobet, and Porat, which we get to very large area R, not quite the regime where R is proportional to M, which is the one we need here. Then we did the extension of this work, this approach with Abbé and Sberlo-Shpilka. We obtain a regime that gets order M. And then this was further improved by Sberlo-Shpilka, and you will see that this will be important this result will come into the proof. And Samordnitsky found another approach. This is the one based on hypercontractivity that further improve in a different regime the weight enumerator. Now this line of work ended up getting quite close to the conjecture, but it actually, instead of getting to this 1 minus entropy curve, which is the optimal curve, it proved that you can obtain a rate which is bounded away from 1 minus entropy of, instead of epsilon log epsilon, say it's another function. It looks like a root epsilon, root minus 1 minus epsilon. So and at some point it seemed like this was unless you start, if you only stick to weight enumerator bound, it seems like this was maybe the optimal trade-off. It also casted a little bit of doubts whether this was the end of the story, actually. Maybe this was the reason why the problem was remaining open. Okay, now the second approach is based on the sharp threshold for Boolean functions. And here the idea is like this. So we care about what I call GLO for global error, which is the property that you draw a random code word, you corrupt it, which is Y. Now you decode it with the closest code words, and this is not the original one. That's the global error. You could also define a local error event where you just look at decoding correctly one component of the code word that you pick. In the read-more code, it doesn't matter which one it is. You do one more small tweak to the definition, which is convenient, which is that you remove the component that you try to decode from the observation. And this has, in particular, the small notational advantage that now the trivial error is half. If your probability of error local is half, then this is random guessing. If you can beat half, then you do something significant already. And if you don't remove the 1, then because that observation already has an epsilon bias, then you will want to beat epsilon. But if you do refinement argument, this epsilon changes. So that quantity sometimes is simply more convenient to use. And so we will remove the component, and it doesn't change much to the picture. Okay, so if this local error vanishes at least like little o of 1 over n by a union bound, you can get that the global error is vanishing.
Union bound over all coordinates.
Yeah, you decode each coordinate independently in parallel. And then now, read-more codes have lots of symmetries. Their permutation group is the affine group. In particular, they are doubly transitive codes. So what does it mean? The code is transitive if for any 2 coordinates you pick, there is always a permutation that maps that component to this one. And it's doubly transitive if any pair of coordinates you pick, you can have a permutation that maps this to this and this to that. And that's a phenomenon of symmetry. This implies that this local probability of error is the same for every coordinate. So that's why I fixed it to be 1. And this really created a perfect bridge to the theory of sharp threshold. But not for error channel, but for the erasure channel. So that's the channel where instead of flipping coordinates, you erase a coordinate with probability epsilon. And what happens in that case that is quite special is that in this case, the event of making a local error viewed in terms of the pattern of the erasures, where the erasures are located, this is exactly a monotone Boolean formula. So you look at it as a formula in terms of where erasures take place. And this is monotone because if you have more erasures, you're more likely to make errors, like you lose information. So it's a monotone, it's a decreasing probability. And And therefore, you could cast.
What is the monotone function? What is the monotone?
So you define it. So you look at the Boolean vectors. That is the indicator of the erasures, where the erasure happens. And then you look at that event, making an error in decoding one guy as a function of that, and that's a Boolean property. And you work with not the Bernoulli half measure, but the Bernoulli epsilon, so you normalize your basis so that it's orthogonal. But the theory is well developed with for IID Bernoulli epsilon. And so the connection you can do is to these two works. So this one tells you that P-log will have a sharp threshold. And this one, the work of Bourgain-Kalai, uses the fact that there's enough symmetry. And when you have transitive symmetry, you know that the critical width of your sharp threshold that decays fast enough. And actually, it's a little of 1 over n squared you get. And so you're good, almost, it's really a beautiful work. You connect to these tools and you need one more element, that's a few line 2, which is that the threshold must happen at capacity because the overall entropy is conserved. That's another fact you have to check first. But then it's really a beautiful casting into the theory of sharp thresholds, and you get back of the envelope. It's really half a page that from this you get the capacity result.
You want to define sharp thresholds, or because it's a separate topic?
Yeah, I mean, so the sharp means that if you look at this, let's call it.
So first we have some monotone function.
Yes. So you have your monotone function. You know it's increasing. It depends if you look at it as increasing or decreasing. In this case,
that's the x-axis is the number of erasures.
Right. This is the number of erasures. So it's epsilon, which is the erasure rate.
This is the probability of the y-axis is the probability of error.
Yeah. So this will be the probability of error. So it will be increasing. Yes. This is the local probability of error.
Yeah. 1 bit.
And so it will be 1 here. Actually, it will be 0 here. Now, it's increasing, and so you can define the pre-image of 1 minus eta and eta, which is the probability value for the erasures that produces an overall error of 1 minus eta or eta. And this defines the width. So you know that if you put yourself at half here, you are at the critical probability that makes that local error to be exactly half. And now you look at the width of this transition when you are between 1 minus eta and eta. And this is this width, critical width of the threshold, and this goes to 0. This is saying that this function will look like this. Now this goes to 0, but also it goes to 0 fast enough because it could be that it doesn't go. So the good news is that here epsilon is of constant order. So there's not this problem that it could go slower than how the critical scales. But here this will scale, this would stay constant. So the fact that it goes to 0 is already saying there's a threshold phenomena. But you also want this to go to 0 fast enough so that you get the decay that allows you to close the original question, the global error. And that is not true for any property. The middle of 1 over n, so you get a scaling of 1 over n squared. This is because there is enough symmetry in the property. So that's the paper of that is mentioned here, the Kudekar Kumar and it uses. So I cannot talk about all the different angles too much, but I'm happy maybe to discuss also at the end more specific.
Anyway, this will resolve the issue of the erasure.
Erasure case, yeah.
Solve the erasure channel. Reed Miller, Chief.
But errors, the issue is that it's not monotone, and it's not just a tweak. The all 0 code words and the all 1 code words are all valid. So sometimes lots of error for the local event can be as good as no error. So it's intrinsically a non-monotone problem. And so we could not connect to this theory. And for long, we tried to connect and we tried to find ways And I think the best result that was obtained in this direction is a result by Reeves and Pfister that's fairly recent, that could show that the local error is vanishing up to capacity, which is remarkable results. The downside is that the decay is quite slow. It's log by root log n. And so in that case, the local error is not quite satisfactory. So it's quite far from what you need to get the global one, but it's still a major progress, a big result.
It's not by trivial union boundary.
No, you cannot, yeah. Yeah, so they really had to dig into, so they looked at what is called these generalized exit functions, and they did bound with mean square errors, and it's quite a remarkable technical paper that gets to this vanishing. They also use, and this is also related to the last approach, back from Doomer, and we use this a lot with Mean, was a postdoc here at Princeton. We knew that we had to use a bit the self-similarity of the Reed-Muller codes. So here they use just the fact that there are two subcodes that are similar in the Reed-Muller codes to get a tighter bounds. Here Doomer already does some recursive techniques, and so I'll tell you about the last approach on what we mean by recursivity and polarization. So first, polar codes. Polar code is a different approach. So you look at the tensor product matrix 1101. It looks like this with this Sierpinski triangle. It turns out that if you take the heaviest rows in that matrix, let's say rate half again, you take the half heaviest rows. This is a Reed-Muller code also. It's another way to construct the Reed-Muller code. The heaviest rows in weight. So that is another way to view Reed-Muller codes. Take this tensor. That's why it's also easily you can construct it in n log n. Compute this tensor, and
this is the basis for that.
Yeah. If you did so, this is the full set of evaluation vectors when you go all the way down to the degree n. If now you select let's say half heaviest rows, you will have the basis of the Reed-Muller codes for rate half.
It's still the monomial basis. It's just a different way to look at the monomial basis for the
right. So now multiply this matrix to the left by an ID Bernoulli half vector. So that's a random mixture of the entire basis of the full code, let's say. Now we want to subsample some of them. We don't want to take all of them. But for a moment, let's take a mixture of everybody. So the probability of error in reconstructing X from Y, it's always upper bounded by the entropy of X given Y. That's true for any random variable where X is discrete. That's the Shannon entropy, the conditional entropy. The advantage is always the same. When you switch to Shannon entropy, you have the property that the Shannon entropy has the log. So the log of a product is the sum of the logs. So you have chain rules that come into play. And that's very often very convenient to massage how the error events are spread. So this the entropy of the X given Y is the same as the entropy of the U given Y. Remember that they are connected through that full matrix, the U and the X. And now here I'm going to use this chain rule that is specific to the Shannon entropy. So that's the entropy of the ith component of U. So you go top to down in this order, given the whole Y and given the past. So that's a very special way to look at these entropies, where in that order you look at the ith component given the past.
You are independent pointers.
Yeah, independent pointers. Yes, but then you correlate them to create the. I mean, you mix them in the X, and then you transmit to get the corrupted Y. So it's a bit of a different angle. It's going a bit fast to explain polarization here, but the key insight is the following: when you view these condition entropies in that ordering, you get a natural recursive structure. Because if you double now the dimension n, you go to 2n. Each of these conditional entropies is obtained by splitting dimension n into two descendants, and the average is back to where you are. So we can order all these conditional entropies for dimension 2n as the children of each parent of dimension n, where you have an even split. So what this means is that you can have a martingale process that describe how these conditional entropy evolve, and that you get because you have such a recursive structure. And that allows you to prove by Martingale's theorems that this must polarize. This goes to either 0 or 1. Just because you are in a bounded space and you are a martingale. And therefore, these entropies will either have no information or full information, like perfect noise or no noise. And so now if you only retain the coordinates that are 0 here, you drive this probability of error to 0. So in other words, you select the rows that have a low entropy to create your code. So it's no longer the read-molar codes because it's not obvious that this selects the same rows as the read-molar codes. And in fact, it's a different code. The beauty is that it gives you another construction that is proof to achieve capacity, because by the balance equation, you must have the right number of coordinate. And then you can even have an efficient algorithm, which is like a huge bonus that we're not discussing here.
Oh, but is the code explicitly described? I mean, you described it in these terms. It's not clear which role monomial you take as your basis.
So it's at the end it's explicit, but there's the usual question that I heard here, like what explicit means, right? So it's explicit, but it's okay. There's a few things. So first of all, it's not the same code construction for different channels. It's not the same for errors or for erasures or for Gaussian noise. So it's now channel dependent, the construction, because you need to combine these entropies. You cannot, the computation of this, the exact computation is actually NP-hard. I think it's not known, but an approximation, each time you back off from capacity, you get a little wiggle, and then you can find an algorithm that computes these conditional entropies.
So given n is polynomial in n.
Exactly, but you need to back off and you need to check how it scales with the back off from capacity. The drawback, so it's a beautiful, it still gives a construction that achieves capacity. It was a major breakthrough. The drawbacks is the fact that you use the universality. It's channel dependent. You get a slightly more involved, albeit efficient encoding. You get a worse distance than the read-molar code. It's not as good, the minimal distance. We said it's not what matters for average case. It's true. When you care about applications, which I won't discuss today, and you look at short block lengths, this sort of comes back into the picture. And then you have this other thing called the scaling law, which is worse. But the point is, it really strengthened the belief that the read-molar codes should also achieve capacity, because in a sense, read-molar codes are, in terms of performance, better than the polar codes. So we knew they had better figure of merits and scaling errors. So it was surprising if the read-molar codes would not achieve capacity. So what we did in Fox 3 years ago with Min is we first tried to see if we could use polarization theory to prove the conjecture. And what we did, so we went back to this picture, and we, instead of going in the order of that matrix, which is a polar order, we went by proceeding on the chain rule is true no matter how you parse your indices. So we decided to parse it from the heaviest rows to the lightest rows, which is a different ordering. And we could still show the read-molar ordering, and we could still show that it polarizes, which was good news. And in fact, it's not a martingale anymore, but so you lose the balancedness of the martingale, but it's a faster convergence. It's just no longer a martingale, it's a super martingale. But the thing that remains open is to show that although it polarizes, we also want to say that the 0 is on the heaviest rows. That means we should select the heaviest rows as the code. And it seems to be true, but it turned out to be pretty hard to prove. And in fact, more recently, we could prove that it's not equivalent to Freiman-Ruscha. It's definitely not equivalent, but it's implied by Freiman-Ruscha conjecture. What you need
conjecture in arithmetic number theory.
Right. So the question in Freiman-Ruscha is that you have a set. In our case, it's a subset of the hypercube, and basically you ask how does the subset behave? So when you add any two vectors in your set, and if the size of that subset is close to the original size of the set, then you would think this is implying the set is not too far from a subspace, and measuring the not too far is what enters this kind of conjecture. And the polynomial Freiman-Ruscha conjecture says that there's some blow-off factor that's of order polynomial, and this is open for many years. And then there's a result by Tom Sanders that proves a quasi-polynomial version. It's not exactly polynomial, but it's quasi. So what you need to close this program from polarization for the read-molar code is it's enough to have a quasi-polynomial, but the exponent is quite close to it. So instead of log in the exponent, you use log 1 plus 5 or something like that, divided by log n. So there was a program here at IAS on additive combinatorics. My colleague Brian Richter was here. I emailed him, we need this generalization of Sanders. Can you please check? And it came back saying that this would be as close almost to proving the whole conjecture. Like it didn't seem to be, it seemed to be closer to the full conjecture than the improvement here. And so we were pretty sad to get that email. Okay, so the state of the art was the following. Here, this approach seems to saturate before the capacity. Here it was either specific to erasure or with a very slow decay. And here we were, at least this was good news and still, because I believe the general belief is that the Freiman-Musha holds. So this was, because at that point we were almost wondering whether it could be that this is a weird problem where you don't get exactly capacity with Reed-Muller for errors, you stop just before and this is tight. And then you just locally have this very slow decay, like some phenomena like that. But that, although it didn't make the proof more close, it kept the belief. So the proof is based on what we call boosting arguments. So boosting is used here in the broad sense. The concept is essentially that we will get a successive refinement of the decoding of a component in the code word. And the reason why it's natural in the Reed-Muller code setting is because there's these strong self-similarities in the code. And so it's a framework that seems appropriate for this kind of argument.
So basically shooting to prove that the local error is less than 1 over.
Yeah, so so we will prove an exponential decay on the global and local error. Yeah. So, but we will start. So this is why boosting is important in the sense is that instead of trying to shoot for this directly, we will ask for very little at the beginning. We will just ask for beating half for the local error, which is something that in coding theory, we never really cared about asking because it sounds silly. Like you don't want, if at least in the average case setting, that is somehow related to the data transmission applications for historically, it was not really interesting to beat half. There's no communication scheme that relies on beating half. Now, in mathematically, it still makes sense. It's the first time you get a non-trivial errors. And then once you go in the idea of boosting in the back of your mind, then it becomes very interesting. So we need a base case, which will be beating half. And we will also need a way to combine and boost with a proof, which is the more difficult part. Last minute edits to the slide.
The base case you don't have for this earlier results that you mentioned, like log n was
right. You can use that for the base case. That's a shortcut you can take, and that's a very good base. We had our own base case, which also has the benefit to generalize to any code that is symmetric. So this is the first lemma. It's width threshold for any symmetric channel. Doesn't have to be the error case, but think of the error case because I did not define the other ones. And for any symmetric code, so it applies to Reed-Muller codes, but the only property you need is that the code has a local error that is coordinate independent. So that follows by transitive, doubly transitive codes, but it could be any other code. What you get is that the local error is always better by half as long as the rate of your code is below the capacity of the channel. So that's the quantitative bound. In fact, you can also prove the other side. So basically what you prove is that there's a width threshold. You don't have this the 0 to 1 jump. May not jump like that, but you have something that it goes from below to above half at capacity. So you have a width threshold.
Not really monotone, right?
Yeah, it's not monotone, you're right. So, yeah. So in the limit, it will go above half, but it could happen in weird rates. Yeah, so that's the important point, is that this, it's still hard to prove directly a real threshold because you don't have monotonicity. But the good news is that even if you give away monotonicity, just by symmetry, you still have this weak threshold. And the proof is not very technical. It's probably, I don't view this as the strong technical contribution of the paper, because I'm sure if we combine 4 papers, it must be something that has been around, I imagine. Although it's written nowhere, it's more conceptually that we didn't think enough of bidding half. Okay, so here is the proof and how it. The first thing is entropy bending, which means if you are below capacity, then you know that the entropy of so Y is the corrupted code word. It's not going to be trivial. What does trivial means? If Y had IID Bernoulli half components, then it will grow. It will be exactly n entropy because it's n independent bits. And that you would get if your channel is completely noisy. If you flip the coordinates with probably half, then your output is IID Bernoulli half still, and so you get an entropy of n. As soon as you are below capacity for your code, you are also scaling with a factor which is slightly below n. So this is done formally by chain rules and things, but it's quite natural to get. Now you do that trick, which is we use the polarization ordering. It's just a chain rule. We just count the entropy by looking at the ith component given the past. And because this overall entropy is less than n times this, there must exist at least one component which is below 1 minus c. Now, if the entropy of one component given the past is better than 1, it means there's something non-trivial here. The entropy of 1 is a Bernoulli half bits. And if it's the conditioning can only reduce the entropy. So entropy of exactly 1 means that you are independent of the past and Bernoulli half. If you're strictly below 1, there's some information that's hiding in that component. But that's not exact. That's more in this polar view. But then by symmetry, you can connect that to the event we care about. So we care about decoding the ith bit in the code word given the noisy observation of the other components. That's our event. We want to bit 1 here, which means we bit half for the property of decoding. And so what you can always say is that if you try to look at the entropy not of the code word, but it's not the corruption, you increase a bit the entropy. That's a line argument. Here you use the symmetry. That's for any I. And because of the symmetry of the code, this is the same as that specific J for which you could exhibit that as a non-trivial performance. And now you're good because conditioning can only reduce its entropy. So if you don't see everybody but J, but you look at the past, you exactly connect to what we had here. So we get something else.
So this is a non-asymptotic result.
Yeah, correct. There's no asymptotics here. Yeah.
Right.
Yes. Yeah. Yeah, it just means that as long as you back off from the capacity.
Right. From the maximum usually.
Right. Yeah. Yeah, so essentially the already being below capacity means that locally you must be something non-trivial. So now the whole game is, so we have a starting point that is only due to symmetry. And now the game is to try to boost this. So usually if we try to vote and you have multiple agents, and each of these agents bit half and their error is better than half, then if the agents are independent, of course you get an exponential improvement of your error probability by doing majority votes. So we'll try to play that game. And so we will look at the slightly bigger real molecules. And the nice property is that real molecules has a soft similarity. If you restrict yourself to not the entire Boolean hypercube for your evaluation, but only to a subspace, for example, you zero out, you freeze to zero some set of the coordinates, then if you evaluate only on that subspace, you also get a real molecule with a smaller n. That's the property that is very good. So if you take 2 disjoint subspace that must contain the whole 0, and let's say that, so this is the first component in your code word. So in the Boolean hypercube, it's indexed by the whole 0 vector. If you here bit half and here you bit half, you can now merge those 2 votes. Because these are all real molecules, because you want to prove at the end of the day, you can come up with a recursive argument. So of course, we don't want to do this with only 2 because that's not a good improvement. We want to do this with as many possible subspace as possible. And so there's a very nice combinatorial question that came up, which is how do we pack subspaces in the whole Boolean hypercube in a way that they don't overlap too much, and also that we can control, the majority votes. And then the structure that really came to rescue are sunflowers. So we know that we cannot afford to have no intersection. There's not enough subspace you can pack that don't intersect, besides for the 0 coordinate. And so you cannot get a boosting there. So you have to concede somewhere, and by choosing a sunflower structure, you can concede only in one subspace that contains all the overlap. So it's like analytically very convenient. Because what is a sunflower? It's simply a collection. So here it's defined for subspaces. Classically it's for subsets, but it's a collection of subset that any pair intersects in the same sets. Here is subspaces, and any pair intersects in the same subspace. And it turns out that you can pack quite a few of these petals. So these are called the petals, and the intersection area is called the kernel. And so if you choose now 3 parameters, so M is where you are in your recursion, M overline is when you want what you will want to decode for your improved performance of the bigger real motor codes, and M lower bar is the dimension of your kernel, where you will concentrate the overlap that you will have to study. It's not about overlap. And you can still pack exponentially many petals in this way. That is not requiring a sunflower lemma. This you can readily build, even efficiently. So we don't need much of the sunflower lemma techniques. It's really the structure that is coming into play. And so think of basically this lower bar and upper bar will be essentially the original M plus some root M and minus some constant root M. So this is essentially like 2 to the root M petals. And the good news now is that when you try to analyze the performance on each petal, you beat half by the base case. If the kernel is a root M dimension, you hope that these dependencies are not too bad, and so you can get a good boost. And you can make
M bar is root M, or M bar is M minus root M?
M lower bar and M upper bar would be M minus root M and N plus root M. Yes. Yeah. So
the kernel is close to M.
Yes. Yeah. It's N minus root M. I said that right. Okay. So you basically now ask about the following question. This is your local error. Write it by conditioning on the kernel. V is the kernel. In expectation over the kernel, you know that this is better than half. Because you have to do boosting, it's not enough to just have that in expectation, it's good over the kernel. You need that with high probability, you have a good enough kernel. Because once you freeze the kernel, those petals become independent, that's the whole point, and so you get the boosting. But now, once you've frozen the kernel, you have to make sure you don't deviate from the expected performance and that you still have with high probability a good kernel. So now you have to do a concentration analysis and show that the kernels with high probability are good ones, in the sense that, so I define here, this probability is the error probability when I condition on freezing the kernel. That's why the M lower bar shows up. So we want to show that with high probability, I put Z prime because it's a restriction only on the kernel of the noise. The noise cannot behave too badly on the kernel, and that you still have a non-trivial base case, even if you condition on the kernel. That this, you can do the boosting. So that's where the free analysis comes into play.
Before this, the intuition is that, can you go back? And the intuition is that even on just root M coordinates, you get the bias if you go below capacity. Right. The key thing is that if you freeze all but root M of the coordinates, you still get a bias if you go below capacity.
Yeah, so that's a good point. The root M doesn't change your rate if you're below capacity. You still you get the same rate. It's not affecting your rate exactly. Yes.
Root M is the best you can do.
Yeah, essentially it's the best. Yeah. Okay, so then I'll go a bit quick because we have 5 more minutes. So the classic. So you want to prove concentration. Classically, you go to second moment bounds. So this is Chebyshev inequality. You use the Fourier wash basis, so you're dealing with a bias measure, but we still have the characters basis that is well defined. So this is Parseval inequality because we say in the second moment, I remove the sets to be empty because I look at the variance. Okay, so if I don't put this is exactly the second moment, when I remove empty, I'm subtracting the mean square. So this is just this bound here that we want to show is smaller. Now this is important, the constraint, because we are conditioning on the kernel, we only look at subsets that are contained in F2 M lower bar. That's the conditioning, the effect of conditioning on the kernel. But I want to view this as acting on the entire space. So if you look at this measure, that's when I freeze Z prime for the kernel. If instead I put QM and N, so I take the kernel to be everything, then I don't average out on anything else. And that's my original probability of error for a given vector. Okay, and then when you put an M lower bar, it means you're averaging out on the other components. So here I'm writing this expression in the ambient dimension M. So that's the original probability of error. But I'm imposing the fact that I must be in the subspace by putting an indicator. So that means that anything outside of this S has to be zeroed out. I don't take contribution outside of the kernel. That's a rewriting of what we have here by writing the measure to be the entire measure, but encoding the condition on the kernel in the fact that the subsets have to be zero outside of the kernel subspace. If we can prove that this is much smaller than the quantity where I remove that condition, that I have to be in the subspace, then we're in good shape, because this is again the second moment of the original probability of error, which is anyway at most 1. So it's a number between 0 and 1. The second moment is less than 1. So if you are much smaller, then this is something that's vanishing. So what this means intuitively is that we want to show that most mass of this probability of error of your original problem for the local quantity is not contained in small subspaces. Because if the mass could be contained in small subspaces, you could be unlucky that it gets into the kernel and you get some atypical event. Now, the reason why this does not happen is the symmetry. The fact that you have symmetry, you must be spread out nicely over your Fourier coefficient, so you don't expect that you could, by poor luck, concentrate on small subspace. And so the critical lemma here uses the symmetry. You pack these coordinates that are in the same equivalence class. And what is the equivalence class is the affine group. So each time you have two sets that are connected by an affine transform, they are treated the same way. And you only care about the fraction of these that are in that low subspace dimension. And so this ends up being a bound that computes the probability that if you have a random set and you look at an affine transform, it stays in a small subspace. Okay, so but intuitively, that's exactly the intuition of Abbé, is that because you're very symmetric, you're going to be spread nicely, and so you can be contained in a small subspace.
But it's still not such a small subspace, it's just codimensional all the time.
Right, so this is not so great. It's much better than, okay, it improves on what we had before, but it's not enough, because we want this, right? We want 2 to the minus m little of this. And so we are not,
It's Bourgain.
yeah. So it's not enough, it's vanishing, it's much faster, but it's not sufficient. But this is again the benefit of boosting our self-recursive argument, is that we've done this once with one sunflower, but now we can put sunflowers on top of sunflowers on top of sunflowers. Okay, so I'll go very quick, and also this is where the most technical part of the proof comes in, and this is also where the amazing work of Colin Sandon comes in. And if you're interested, I think he should be here to talk about this. We cannot just do L1, L2. We need to go to L4 estimates just to buy a log m here. So by doing the whole recursive scheme and doing a much tighter analysis, you get the log m here, which seems like, again, we're still far from that. But the last piece is that it allows to connect to the original line of work on the weight enumerator. The fact that you get such a error probability locally means that you know that if you decode each component locally, you must be that you're not too far from the true code words, and you have a notion of the radius of where you should be coming from these local bounds. If you redo these weight enumerator bounds that we saw at the beginning, having this extra information coming from this local error, it turns out that the paper of Sberlo-Shpilka gives you just a bound that gets to the vanishing rate for globally. So you can actually combine the original weight enumerator bounds with this extra local analysis, and this gets the full conjecture. And it was quite, this was just for anecdote. So not only, these two papers were quite similar, but we need that improvement over this one. And not only we need the improvement, but when we looked at the theorem statement, it was still not enough. We had to look at really in the middle of the proof, there was the right inequality hiding. So everything was just by, at the end, it really looked like this. The improvement here was a log n, because m is log n, and it just fit exactly page 17 of that paper, and there was nothing left there was no margin. So at the end, once then we keep doing boosting on top of that, and so all together you get an exponential decay in the square root of n. And you can do it efficiently from the base case if you're satisfied with an exponent which is 2 to the root m, and otherwise, if you want exactly 2 to the minus root n, which is optimal, you do it information theoretically using other bounds. So that's the end. They achieved the capacity on any symmetric channels. I only discuss here the error channels, but the proof technique applies to any symmetric channels, and they have this n log n deterministic encoding. Efficiency of the decoder, we need the efficiency of the base case. We need to bit half efficiently, and then the rest is efficient, but the first part is still open. So I mean, the classic statement here is that the Shannon was in 48, those codes were in the 50s, and it just took a lot of time to realize that they were optimal, and now we also realize that they are quite good. So we implemented with the boosting, and this seems to work. So there's actually a company who was really invested in using those for potentially communication applications.
And what they do both for search for the process.
Yeah, because base case is the lower dimension, and people care in applications for even 256 in some applications is already good enough. 1024 is. And so when you do the boosting, this takes you to maybe 8th dimension, and then you can brute force the base case. Yeah, and so it's still not polytime because the base case will not scale, but practically you can do it, and the boosting then is done efficiently. Okay, so I didn't talk about all the applications in computer science of the read-only codes, mostly in worst case, but okay, it was fun to show this connection with different branches of the discrete maths, and now we are rewriting a bit the paper to simplify some parts. Okay, thank you.
Thank you.
Questions?
Yes.
So for the erasure channel, the double transitive is the only thing you need, right?
Exactly. Yeah.
And is there a chance this would also be enough for this?
Yeah, very good question. So base case, we already have it for any double transitive. What we need now to also get for double transitive is to do the boosting. So and it's a nice question that looks like this. I give you a code that is double transitive. And if you can show that when you restrict yourself to, you can come up with petals. By the way, I should say the sunflower was a good structure to control the analysis, but in theory you could use different kinds of flowers. So more generally now you are looking for petals, meaning collection of subsets of coordinates that will have the property that you have to ensure that you still have the base case on enough of them, and that they don't overlap too much. If this follows from enough symmetry of the code, then we will also be able to do the boosting. And so now it seems like this works for some other class of codes, but it also seems like there is a more general phenomena that enough symmetries give rise to the existence of good petals. That's something we work on. It's not obvious if it will be as general as any doubly transitive codes. I'm confident there will be something between read-motor and all doubly transitive. I'm not sure how far it will go, but potentially all doubly transitive is hopeful. But there are new combinatorial questions that come up.
So for non-symmetric channels, you essentially have also the result, because linear codes are not optimal for those because their empirical distributions are not 1/2.
Exactly.
They wouldn't maximize mutual information, but there is this technique by, I think it's attributed to Gallagher.
Yeah, the trick.
I think Andy Yao also did some. So essentially the idea is to generate an arbitrary distribution from binary coin flips, from aggregating binary coin flips. So you aggregate several linear codes, several read-motor codes, and then you will achieve capacity.
Right, this is called Gallagher trick, right? if your input distribution is 1/3, 2/3, then or if it's at least maybe dyadic, then you create some mixture that gets to yes. So you could use that.
Yeah.
But otherwise, you're right that like polar codes. Otherwise, you basically have to do some trick on top of that to get to asymmetric channel. What this generalizes to nicely is a QRE symmetric channels.
Yeah.
And there, because polynomials are everything is well defined on QRE fields, the proof go through if you have a QRE symmetric channel, which is also a good feature.
Yeah.
Yeah.
So there is no other code besides Reed-Muller that you think maybe a good candidate to apply the boosting?
So BCH codes, I think, is another option, or mostly polynomial evaluation codes. I think generally, if you have some symmetry and you are a polynomial evaluation codes, I think you could generalize a bit more. I was hoping that the cyclic codes also could work, but for that we need the question of before. It seems like just symmetries should imply existence of good petals, but it's not clear yet what's the structure, if it's a bit transitive or not. But the boosting at the same time is something that I think is going to be usable because there's a trade-off here. There's a proof and there is the applicability. And the Reed-Muller is so nice that it fits for the proof, but for the applicability, I think it can be used a bit in a broader way if you don't care for proof.
More questions? All right, thanks.
Thank you.